Good afternoon. My name is Advait, and I was working at the Atlas experiment, working on the reconstruction of three-prong taus. Here's a clicker. Yes, I was doing this project under the supervision of Dr. Christian Grefe, and I'll be presenting the things that I found out. So first of all, what is a tau lepton? So it is a particle in the lepton group of the standard model, and it is on the heavier side of leptons. It is in fact the most heavy lepton, and with a greater mass also comes a shorter lifespan. And as you can see, the lifespan isn't particularly long. So instead of measuring the tau lepton directly, as one would do, for example, with a muon or an electron, one has to instead analyze the decay products of the tau lepton. And on the right, you can see different decay modes of the tau lepton. It has a leptonic decay mode, where it decays into other leptons, muons, for instance, and a hadronic decay mode, which makes the majority of the decay modes. I'll be focusing on the three-prong decay mode, which makes up 14% of the decay modes. And here on the left, you can see what a hadronic jet looks like. So when the tau lepton decays hadronically, it produces a jet like this. And in 3 dimensions, it takes the form of a cone, which can be seen in the different calorimeters. So as I mentioned, the three-prong tau decay, I'll be focusing specifically on the one where the tau decays into a A1 meson, which is a pseudo-vector meson, which means it's not really comprised of well-defined quarks, but instead it's sort of a mixture of a lot of quarks and can much better be defined by its properties or its flavor properties. And it has a resonance at 1.2 GeV. So ideally, as can be seen by the simulation, one should see a peak at about 1.2 GeV. And this would be the proof for this particle. So as I mentioned, I did my project at the Atlas detector, and the Atlas detector is the biggest detector at the Large Hadron Collider Complex. And it consists of the inner detector, which holds the pixel detector, which works via the semiconductor principle. Then we have the electromagnetic calorimeter, which triggers the decay of electromagnetic particles. So particles that decay into electrons or photons, their energy is absorbed here. And for hadronically decaying particles, so for them, you also have a signal in the electromagnetic calorimeter, but if they decay further, and you also have a signal in the hadronic calorimeter. And then on the edges, these sort of plates, those are the muon chambers. So if a muon goes through, it leaves an energy deposition in these muon chambers. So the signal I'll be looking for is for the leptonic decay, I'm expecting something in the electromagnetic calorimeter or the muon chambers, since it's either an electron or a muon. And for the hadronic jets, I'm looking for a signal in the hadronic calorimeter. So to produce a simulated data that I showed previously, we use the Monte Carlo principle. An example of this would be to find the ratio of the area of a circle and that of a square. One could use pi and all the formulas that we learn in school. But what you could also do is generate random points and just find the ratio of the points that landed in the circle and the ones that landed outside the circle. So this allows you, well, this is quite a simple example, but in more complicated examples, this allows you to simulate very complicated processes. And the signature that I'm looking for is a tau lepton that decays hadronically and leptonically. So this leptonic decay would be a muon in the most part. And so what I'm looking for is a muon and a tau lepton candidate. The criteria that I have for the muon are that it has to be isolated, so it shouldn't be part of some jet. The tight muon isolation means that I want to cut away as much background as possible. While I also will be cutting away a lot of signal, I will be cutting away more background than I will be signal. That's why I have a tight isolation. And since the Z, which produces the tau lepton, the Z boson, is neutral, I would expect my decay products to have opposite signs so that the signs add up to 0. And the relevant backgrounds for this decay are the Z to mu mu, where one of the muons is accidentally reconstructed as a tau lepton, and that produces the signal. Another background decay mode would be the W to mu nu. Here I have one muon, and I reconstruct an additional jet and constitute it to this decay. And then I have QCD jets, which are just non-tau jets. So here I have the selection decay modes. This is without any filters applied. So I see the mass of the ditau, so both taus, and I can see that the z to mu mu decay mode has a very large contribution to this, but also the z to tau tau, which I am looking for, also contributes to this. And then here at the bottom, I have QCD background and also a little bit of top core background. Here I see the angle eta, or the pseudo rapidity as it's called. We can see that there's a spike in the z to mu mu decay mode. This is because at around eta equals to 0, there isn't actually a muon chamber in the atlas detector. So you're more likely to falsely reconstruct a z to mu mu decay as one of our signals. So this is why we see a spike there. And on the very right, we see different decay modes and how many entries we have for them. So I'll be focusing on 3 charged particles and 0 neutral particles. So that's 3, and that's this decay mode here. And later on, we can filter for this decay mode so that we only see those. Exactly. When I filtered these out, the ditau mass becomes this plot here. As we can see, the contributions from the muon decay mode almost vanish. And instead, we just have the z to tau tau, which is what we were looking for, and then this QCD background. The data points are in black here. And as we can see, it fits quite well. Now, what we can do is, since we're only looking for z to tau tau decay modes, we can just cut the data here because we're losing not a lot of signal, but a lot of background. And so when we cut this off and we look at the single tau mass, we see this beautiful curve here, and it fits the data quite well, and we only have a minimal background. Now, I was not only looking at the high energy tau decays, but also at the low energy ones. So this is between 6 and 10 GeV. And what we were doing up until now is reconstructing tau jets and getting the tau information from there. But as we can see from this efficiency plot, efficiency being the number of candidates we have plus the ones we exclude, so the inclusive and the exclusive divided by only the inclusive. So how many events are we throwing away because of our signal? And so here we can see that if we were to continue doing the tau jet reconstruction between 6 and 10 GeV, our efficiency is quite low. Where instead, if we were to look at the muon or at the pion tracks themselves and reconstruct the taus directly from there, we can see that our efficiency is much higher at these low PT, PT being transverse momentum or the momentum in the transverse plane. It's around 0.65, whereas this one, even at high PT, only peaks around 0.45. So it's much more efficient to go from the pion tracks to the taus than from the tau jets to the taus. Right, and since it's quite hard to go through thousands of data or events and filter out the ones that fit to our selection, it's easier to use a tool such as our data frame. Our data frame is a class in root, which is described as being a Swiss Army knife for data analysis, meaning it's a very helpful tool that speeds up analyses, and it uses a tabular structure where our rows are the events and our columns are different criteria like 4-vector or D0, which I'll get into later. Right, so we have our efficiency plots for the PT of the truth pion, truth pion being the simulated one. And as we can see, if we reconstruct from the pions, the PT efficiency is quite low for a transverse momentum less than 2. So what we can do is just make a cut here and only accept pions with a transverse momentum greater than 2. Right, and so for our track selection, we also have the condition that eta, or the pseudo rapidity, has to be between -2.5 and 2.5. This is because these are just the edges of the detectors, and so that's why we scale it in like that. PT greater than 2, as I mentioned, and D0, which is the distance between the point where the tracks meet and the point where our tracks or where our track starts. So where the proton beams meet and where our reconstructed track starts. That the difference in that has to be less than 0.1 for efficiency reasons. And since we're looking at 3 pion tracks, we can't exactly know which ones belong together. So what we do is we do a combinatoric of all of them and then simply apply our conditions to all of these combinations, and the ones that get through most likely belong together. So the sum of the charges has to be -1 because we're adding a negative pion, and a positive pion. And the mass of 2 of the pions that are oppositely charged have to be around the rho mass, because as we can see from this Feynman diagram, the A1 decays into a pi minus, this and a row, a neutral row. This neutral row then decays into a pi minus and a pi plus. So in the end, we have these 3 pions I've been talking about, but 2 of the ones with the opposite charges have to equal around the row mass. And here we see a plot where on the left we have simply the simulated data, and here we have a reconstruction of the real data, but using the simulated data to identify which of the 3 pions belong together. So we're kind of cheating by using simulated data to get the real data. So this is what sort of a perfect reconstruction would look like. Well, it won't look like this in reality. As I mentioned, the mass of 2 of the oppositely charged pions has to equal around the row mass, and the row has an invariant mass of about 775 MeV, and we see a peak here, which means that a row meson was produced here. And since we only have 2 pi's and less filters, that means we have more events, and we have about 4,500 at the peak. Oh, went one back. Exactly. Now we have the actual reconstructed mass plot where we expect to see a peak at the A1 mass, the A1 mass being about 1.2 GeV, and we see a peak around that area. The plot could be better, and it could look like the optimal plot that we saw, but better optimization would be needed for this. And so in conclusion, the zeta tau tau decay has a clear A1 resonance, as we can see from the data, both in high energies and in low energies. And the Atlas reconstruction is usually tau jet based, but here we also saw a pion track based reconstruction. And we're able to re-identify physics processes, so like we saw the mass, the row meson mass and the A1 resonance. And as a layman, I would say, I think we have it. But as a scientist, I would say, this is not the end of the rabbit hole, because the next steps would be to refine the track selection and the 3-track combinatoric selection and get a better plot than the one we see here. So as mentioned, there is room for improvement. The lessons I've learned during this project is that one has to apply optimum selection filters. So only apply the filters that are absolutely necessary, because we can't afford to lose events, because especially when you're dealing with low energies, you simply don't have a lot of events. So you have to be really careful what you throw out and what you keep. Efficient coding is something I learned to do the hard way, because you want to write code that you can use a week later and not just on that day. Because for my code, a lot of the time what happened is that I couldn't use it after I was done using it, because I'd written in a way that couldn't be reproduced. So it's important to do clean coding and testing with less data to save time and CPU power. So my data set was about 25 gigabytes big, and I wouldn't recommend using all of that data to just test if a plot works. So just use one plot, check if it works, and then you can scale it up later. And that will save you a lot of time. And that is the end of my presentation. Once again, I'd like to, I'm very grateful to Dr. Christian Refe, who took me under his wing for these 2 weeks, and I've learned a lot under his guidance, and I'm very grateful. Thank you.